Hello, this is the hopefully less boring math tutor. Today we're going to be talking about tangent and normal vectors to a curve. That's tangent and normal vectors to a curve. And tangent and normal vectors, they're going to show up all over the place in math and physics. So you're often going to find yourself in situations where you need to calculate each one and use the resulting expressions to calculate or measure work, or maybe you're measuring force. And even sometimes you're going to be using them for longer multidimensional optimization calculations. So you might do this in artificial intelligence or places like that. But either way, in these cases, you're going to want to use them in their unit vector form. Unit vector version, what we mean by that is just the vector that's scaled down to a single unit of magnitude. Single unit of magnitude. And the problem with calculating these unit vectors is that they can be very messy and time-consuming to calculate. And our goal here in this notebook is to better understand the steps for computation, when you're actually doing this work, and then to write a simple Python program that'll do that computation for you. To simplify things a bit, we're going to be working in 2 dimensions instead of 3. So let's talk about what we mean by that. This is 3 dimensions, and we have a normal vector here that is normal to this curve. If you imagine there's a tangent plane to this sphere that sits right on top of that sphere as a tangent plane. The normal vector is going to be exactly perpendicular to that tangent plane. And so you can see in this drawing here, there's 90 degrees from the tangent. That's a normal vector in 3 dimensions. But we're going to be talking about normal vectors in 2 dimensions. They're a little easier to work with when we're just getting into it. And so you can see we've got one right here. The green line here is the tangent vector, so it goes tangent to the curve. The red line, the red little arrow there, that is the normal vector. And the normal vector is exactly perpendicular to that tangent vector, and it always points concave in to the curve. So you can see the concave part of the curve, it's pointed in that direction as opposed to this other direction here. So that's what we mean by tangent and normal vectors. So as we go back up here, let's talk just for a little bit about what a norm of a vector is. So the easiest way to think about a norm is the way you think about the Pythagorean theorem, right? So you've got a squared plus b squared equals c squared. So in this case, u1 might be a squared, u2 is b squared, and that equals c squared. And so if you want to get what c squared is, it's basically the square root of u1 squared plus u2 squared. Pythagorean theorem is really all that is, and that's what we mean when we have a norm. And you always put the norm of the expression as the denominator when you're doing a unit vector, and that scales things down into that single unit. And this works, in 2 dimensions. We're talking about 2 dimensions here, but it also works in 3 dimensions. You can see some examples here that are multidimensional. Here's one in R4, and you can see just all 4 of those dimensions are squared, and we take the square root of them after we add them together, and you've got that norm. Works just like the Pythagorean theorem, multiple dimensions. So there you have it. That's what we mean by the norm. Don't get that confused with the normal vector. The norm is that magnitude. Okay, so let's talk about the steps. I'm going to talk about the steps here. So we've got 3 steps when we're trying to calculate these tangent vectors and these normal vectors to a curve. So step 1 is kind of just parameterizing the curve. So we're assuming that we start with a function like f of x equals x squared. So the kind of functions we were used to dealing with for our whole lives, y equals some expression of x. We need to parameterize those and turn them into a vector value function, and you do that by parameterizing them. In this case, we're using the parameter t, and you can see that once we parameterize it, then we're just dealing with those vector value functions from that point on. So if we get to step 2, we've got our vector value function r of t, that is that parameterized representation of the original function, and we calculate the tangent unit vector of that by taking the derivative of r of t as the numerator, and then the norm of the derivative of r of t as the denominator, and that's going to give us the tangent unit vector. And then when we want to calculate the normal vector, we take the derivative of this tangent vector, and we put that in the numerator, and in the denominator, we take the norm of the derivative of that tangent vector, and we put that in the denominator. And you can see how that might, with all those square roots and adding squares together in there, that's some pretty messy derivative computation there, and you can see why they can be frustrating to a lot of math students, including myself. So let's try an example, and you'll see what we're talking about here. So step 1 is, well, for step 1, we should talk about what's the actual function we're doing. So the function we're doing is f of x equals x squared. We're all familiar with this parabola. You've been looking at it probably for many years, ever since Algebra 1 or Algebra 2. You're familiar with y equals x squared, so that's the function we're going to use. And step one is we're going to parameterize our curve. So the way we parameterize our curve, we're going to take t equal to x. And if the parameter t is equal to x, then the expression for y in terms of t is just going to be t squared, because y equals x squared, then y of t equals t squared. And so then we have our vector valued function. Our vector value function r of t is simply the t for the x component of the vector value function, and t squared for the y component of that vector value function. That's r of t. So we've got our parameterized curve, r of t, it's t squared. And then we can move on to step two. Step two is where we calculate the tangent vector. So the tangent vector is a little more tricky, because we have to take the derivative of r of t, and we have to put that in the numerator, and then we take the norm of the derivative of r of t and put that in the denominator. And so to do that, we can do the math right here, and we take the norm here by saying the derivative of r of t is 1, 2t. So the x component is 1, so we say 1 squared, plus the y component, which is 2t, so we say 2t squared. So that gives us our denominator of 1 plus 4t squared, and the square root of that is our norm. And then in the numerator, we just have the derivative of r of t, which is 1, 2t. And so now we've got our tangent vector. We can start calculating our normal vector. And our normal vector is we have to take the derivative of this tangent vector and do the same thing with it. And that's where you can see it gets a little messy and tedious. And so to make things easy on ourselves, we're going to use the computer. And the computer is really good at calculating this kind of stuff. So let's write some Python code and see if we can get the computer to do it for us. So I'm going to import a bunch of stuff, all the tools we need. I'm going to set up a symbol for t, and then I'm going to use t of t. I'm just going to fill in this vector valued function that we discovered up here. I'm going to go ahead and shortcut things a little bit and just fill that in as an expression, t of t, right here. And then all we have to do to get t prime t is we just differentiate with respect to t each of the components. We've got the x component, and we've got the y component of our vector valued function, and we're going to take the derivative of each with respect to t. And so after we do that, let's see what the computer comes up with here. So for the x component of the derivative of the tangent vector, it gives us this expression for the x component of t prime t. For the y component of t prime t, it gives us this more complicated expression here. And so now that we have that, we can move on and we can compute this normal vector. And this is we basically run it through the same thing. And what do we get? We get this value for the x component, and we get this value for the y component. And so let's visualize these and plot them out. If you've ever used PyPlot before, you know that the first thing we do is we just create an array with all of our dependent variables. So our independent variable, in this case it's t, that's our parameterized function. So we're going to make an array of 100 evenly spaced values from -4 to 4, and those are going to be our t values. So we define our r of t function as a vector valued function. It's t and t squared, like we talked about earlier. And then we do this kind of interesting thing where you need to turn your symbolic math function. This is our symbolic math function up here. We're going to turn that into an actual Python function that can be called. So that's what's going on here with this lambda phi. And we're going to do that for our r of t, our t of t, and then also for our n of t, our normal vector. We did that for those. And then we just go down here and plot them all. So we're going to plot r of t. We're going to plot the two vectors. So this is this vector right here is our tangent vector. And then this vector down here is our normal vector. And then we're going to set the axes to be equal so that they're at the same scale. And that's going to make sure that things look as we want them to geometrically when we actually plot it. So let's plot it and see how it looks. It looks like a parabola, just like we expected, and you'll notice that we've got our two vectors in there. The green vector is the tangent vector, and that points along the tangent line of the curve. You may have noticed up here that we plotted these vectors at t equals 2, which in this case, of course, is x equals 2 because of the way we parameterize our function, and there the vectors are, right, where we expected them to be. And so it's showing the tangent vector along the curve, and it's showing the normal vector just perpendicular to the tangent line of the curve and pointed in concave with the curve. So however the curve is pointed in terms of concave versus versus outside the curve, it's always pointed inside the curve. And it worked, just like we expected. So now what we're going to do is, let's take this code that we wrote and let's turn it into a general function that we can use in Python to draw these curves and these vectors whenever we want to. So in order to do that, we pulled out this little make norm function that creates the norm. Basically, it takes the x component, the y component, and just adds them together and puts them in a square root. So you've got that denominator for yourself. We've got that, and then we did this other interesting thing that was different from the example above, where instead of just drawing the normal vector and the tangent vector at a specific value like t equals 2, we said let's go in increments of 10t and just draw every 10t. We're going to draw the normal and the tangent vector at that location, at each value of 10t, and that way we can see how the normal and tangent vector changes over time and visualize that. So that's our function. As always, you've got this entire collab that you can have a link to in the description for the video, and just make a copy of it, play around with it, run the function yourself, see how it works. So I ran a few tests on it. First thing I did was a circle. So this is our function, drawing a circle. If you're familiar with the parameterized version of a circle, it's just cosine t, sine t is the vector value function for that. And just like we'd expect, we've got our red normal vectors pointed inside, concave to the curve, all pointed to the center of the circle. And then the tangent vector is pointed around the circle, tangent to the circle. And notice that the green tangent vector always goes in the direction of increasing t. That's another thing that these tangent vectors do. They go along with the increase of your parameter. Then we tried a sideways parabola. So instead of y equals x squared, we did x squared equals y, which gives us that sideways parabola. And sure enough, just like you'd expect, you've got that red normal vector pointed concave direction of the curve, and then exactly perpendicular to the tangent line. And then you've got the tangent vector, the green vector, pointed in the tangent direction of increasing t on your curve. Then this one's a little harder to see. This is y equals x cubed, which has that curve that comes up from infinity, goes to the center of our axes, crosses over 0, and comes up infinity on the other side. And it's a little hard to see there, but the vectors are doing exactly what we would expect them to do in that context. And then continuing on, this is my personal favorite, the curve for y equals sine x. So this is just a simple sine curve. And you can see, notice what we've got going on here, like we said. The normal vector is always pointed concave of the curve. And so each of these, you'll notice that the normal vector changes its direction. This one right here was very close to that inflection point. A sine wave has an inflection point about halfway through here, and you can see that's where that normal vector changes. So you can see it actually switched just like you'd expect it to. And then this last one here is on the other side of the inflection point on this downward slope, and that's pointed up because that is where the curve becomes concave in the other direction. So normal vectors always point toward the concave direction. The tangent always points along the tangent direction, or along the tangent line to the curve, and in the direction of increasing parameter values. So there you have it. That is our function. Next steps, we did this general 2D function. It actually should be pretty easy to expand it into 3 dimensions if you want to. If anyone's interested in trying that out, go ahead and copy this Google Colab and make some adjustments to it and send it back to me, and I'll share it out, because I think that would be a great function to have in 3 dimensions. So in 3 dimensions, you would have a tangent plane and a normal vector to that tangent plane of a 3-dimensional shape. So like in this drawing here, we've got a sphere. So see if someone out there can change that function to work in 3 dimensions. I think that'd be pretty cool. All right, have a fantastic week. If you like the videos, hit the like button, and if you are interested in seeing more, hit the subscribe, and you'll be notified when new ones come out. Thank you.